joining us today for a talk by Dr. Stefano Boccaletti, who is our new APS fellow. This talk is part of our APS fellow series. So in a minute, our colleague will introduce him. So I'm going to just go over some business. There will be future events. Please be tuned for emails coming from APS. We have changed our email server. So the emails will be coming from APS. So there will be more events after the March meeting. If you're not a GSNP member, we would like you to join GSNP. There are more opportunities if you are a member of the APS and the GSNP. We are also on the verge of becoming a division, which will have even more opportunities for you. Also follow us on social media, wherever social media takes us. A few announcements. One of them is for our junior members. So early career members are eligible to submit their recent publications for Image of the Month. If you are a GSNP member, you can log into your account on Engage and submit this Image of the Month based on your new papers, and it will be on a rolling on APS website. Additionally, we are looking forward to the Global Summit. GSNP is sponsoring and co-sponsoring 47 sessions. We would like to invite you to definitely look up our short course on Sunday, March 16 on exploring the physics of human social systems. We are co-sponsoring an outreach event, the Squishy Physics Sunday as well. On Tuesday, there will be a mixer for junior scientists. And also I would like to invite everybody to our GSNP business meeting at 6:15 p.m. on the splashy side of the meeting, where we will honor our fellows and our colleagues at the business meeting, and we will have a reception after that. There are more sessions. Please look us up on the APS website. There are prize and award sessions, focus and invited sessions, and we look forward to seeing you. I would like to remind you of our Zoom etiquettes. During the talk, please make sure that you're on mute. If you're unmuted, one of the co-hosts has to ask you to unmute yourself. If you have any clarifying questions, please put them in the chat box, and one of the co-hosts will pass it to the speaker. Other longer questions will be saved for after the meeting. After the talk, you're encouraged to switch on your camera and engage with us. Please post your broader questions and comment in the chat box, and either one of the hosts will pass the question to the speaker or invite you to unmute and ask your question yourself. Thank you, and I will pass it to Arjunda.
Great. Thank you, Shima. Hi, everyone. It's an honor to introduce Stefano Boccaletti for our very first talk of this year at klogW series. Stefano received a PhD in physics at the University of Florence in 1995, but since has also got a PhD honoris causa at the University Rey Juan Carlos of Madrid in 2015. He has also been a scientific attaché of the Italian embassy in Israel during 2007 to 2011, and again in 2014 to 2018. He is currently Director of Research at the Institute of Complex Systems of the Italian CNR in Florence. His major scientific interests are in pattern formation and competition in extended media, control and synchronization of chaos, and the structure and dynamics of complex networks. He is currently editor-in-chief of the journal Chaos, Solitons, and Fractals of Elsevier from 2013 onwards, a member of the Academia Europaea since 2016, and as you just heard, he's a new fellow of the American Physical Society. He was, among his many other interesting achievements, was that he was elected member of the Florence City Council from 1995 to 1999. Stefano's published 350 plus papers and has tens of thousands of citations with H factor of 76 and growing a bit. One of his most important publications is the monograph Complex Networks, Structure and Dynamics, which has more than 13,000 citations. It was published in Physics Reports. With all that as background, we are excited to hear his talk today, in fact, about complex networks and the 6 degrees of separation and how it features in these things. Take it away, Stefano.
So thank you a lot for inviting me, and it's really an honor for me to deliver this talk in this occasion. So let me share the screen first, so that you all are able to see the presentation. Can you see the presentation? It's the presentation visible to you?
No, it's a black screen.
Not yet.
Not yet?
No.
Yeah.
So let me stop and share again then. The entire screen, yes. I'm sharing the entire screen. Now, is now visible the presentation?
Not to me yet.
But we see
yeah,
double.
it worked with.
Mhm.
Sorry.
It says
Yeah.
okay.
Now we can see it.
Yes.
Yes.
Yes. And now?
Yes, thank you.
Yes. Okay. So thank you a lot. Please, in case of any problem, interrupt me, and we will try to solve the issue. So once again, thank you a lot for let me present in this occasion my recent work on the 6 degrees of separation. It's a work that really took us more or less 1 year, and it involved several collaborators all around the world, from Spain to Russia to China to Italy to Slovenia to Chile, because we really needed people from different, extraction and educations, from pure mathematicians. The work includes a series of theorems and strong proofs of what we are going to say, and together with people from social science, because we needed indeed to have a feeling of what is going on. So let me start with the story. The story starts in 1929, and it starts with a novel, not as a scientific issue. The novel was written by the Hungarian writer Frigyes Karinti, and he wrote this story, Chains, in which he describes a game where a group of people was discussing about the fact the members of the human societies are closer together than ever before. And one of these people in the table is actually betting that each person of the Earth population, which was around 1.8 billion people at that time, could be reached by any one of the participants in the game using nothing but their personal network of acquaintances. So it was the first time it was, in a sense, proposed that you can navigate the network of personal acquaintances in a way that you can create chains between people, and the length of this chain actually are very, very small. And actually, in that paper, which coined the expression the 6 degrees of separation, in that novel, the bet was that the resulting chain would be of no more than 5 intermediators, that is, in between you and any other person of the world, there are no more than 5 other people. This, of course, has nothing to do with science. It's a novel. But then, in 1967, Stanley Milgram, for the first time, tried to perform an experiment in which he wanted to test the social distancing. So what he did, he took a sample of farmers in Nebraska, and he gave to each one of them the goal of reaching a specific target in Boston. And the specific target was a broker in Boston. So there was no way for the farmers to know directly the broker. And the idea of Milgram was, let's each one of the farmers to send a letter to one of the person whom he knows and whom he believes it can be closer to the broker in Boston. And then the recipient of the letter had to write another letter and so on and so forth to create a chain. And of course, the letters were copied to Milgram, who could follow the chains. And he actually found that these chains are very small in size, and they are about 6. Indeed, 6 number of steps. The same experiment was then repeated by Duncan Watts with the internet email users, and he could, by means of an experiment which was done by the Columbia University, was able to track 24,000 chains arriving to 18 different targets, not only one, from 13 different countries, and these other experiments confirmed once again that the average number of steps in the chains was indeed around 6. Then several other experiments have been launched on a planetary scale on social networks. For example, 2007, there is a study by Jure Leskovich and Eric Horowitz with a data set of 30 billion conversations among 240 million users of Microsoft Messengers. And this study revealed the average path length again to be 6. Then in 2011, they studied Twitter. There is the first large-scale analysis of Twitter, and it was found and it was announced that the average degree of separation between 2 randomly selected users of Twitter is 3.435. This is something that Elon Musk needs to know because Twitter is now X. Then again, Facebook in 2011. Facebook is the 3rd nation of the world. First nation is India today. Second nation is China. Third nation is Twitter. You have 721 million users with 69 more or less billion friendship links. And the study of Facebook reveals that, once again, the average distance between the nodes is smaller than 6. So this is a consistent proof that social networks have this property of having very short chains. And actually, there is this number 6, which is a sort of magic. And the idea of this study is to try to understand why this number 6 is appearing, if there is a sort of reason for this number 6 to appear. Now, what is the problem? The problem is the following. Now, imagine that you create a network. It is well known that if you create a network and the structure of connection is a regular structure, like a ring, for example, or a lattice, or whatever, then the maximal distance, the diameter of the network, which is the maximal value of distance between any 2 nodes of the network, will scale linearly with the sides of the network. And you understand immediately that if this was the case, one should observe a tremendous difference between the 1,000 person of the experiment of Milgram and the 721 million users of Facebook. But this is not the case. In both cases, you observe 6. So it's clear that the scaling of the maximal distance in social network is not following what is the forecast of a regular arrangement. Then, as it is known in the last 20 years, there was the theory of small world networks, in which you have specific arrangements of the connection, but still in small world network, the diameter, that is the maximal distance, I repeat, between any two nodes of the network has a logarithmic scale. And once again, since you have more than 6 order of magnitude from the 1,000 members of the experiment done by Milgram, the 721 billion members of Facebook, this logarithmic scale should appear. So if you measure 6 in one case, you should measure more or less 20, 30 in the other case, and you don't. So a problem arises. The problem is, how can I construct a network? How can I grow a network? How social network can organize in a way that they produce a sort of ultra small world states. They're not small world in the sense that the distance between the nodes have to be renormalized in a way that the diameter of such structure is independent on the sides. And so this was our motivation. Is it possible to construct a model, a growing model of a network, or just, so to say, an organization model of a network, which allows having a diameter, a maximal distance, which is independent on the sides of the network? And in doing this, as we will see momentarily, we found that you can imagine very simple mechanisms that are determining this property, and the same mechanism give rise to the fact that you have immediately, naturally, the emergence of the number 6. So not only the moment you, so to say, you imply this mechanism, you don't not only have a network whose distances are properly renormalized with size so that the diameter is not depending on the sides, but moreover, you have that the diameter has to be exactly equal to 6. So what you do, the idea we had is, let's us put the minimal, so to say, the zeroth model that is doing this. And in doing this, what we decided to do is to...
May I interrupt you for a second?
Please.
It's not a big deal, but there's a menu bar sitting in front of your title. If you could move it, maybe, it's...
Very good.
Thank you. Some words are missing.
So the idea is to start from what distinguishes social network from any other network. And what distinguishes social network from any other network is that social networks are made of rational agents. So they're made by people, and people decide the connection they want to do according to some rational ideas. So we decided to use a game theoretical approach for the network evolution. So we imagine that people decides to have connection in social network depending on 2 parameters. One is you have some cost involved in forming new connections, and you have some benefit, because forming new connection can give rise to some benefit. And the very simple idea is, let's put together a game in which each individual compare the cost and benefits and decides whether or not forming new connections, depending on whether the cost incurred by the nodes in maintaining such connection is smaller or larger than the benefit accrued. And then, if you do this, you immediately define an evolution of the network, and you can prove this evolution when it goes to the Nash equilibrium, that is, it goes to the Nash equilibrium of the game. You can prove that such asymptotic equilibrium state features a diameter which does not depend on the system size, and it's equal to 6. So to be specific, let me introduce the game. The game is very simple. You are the red woman, And at each step of the game, you imagine that the end nodes of a network are the agents of such game. For example, one agent here is the red human. And at each step of the game, each agent selects, independently of the choices made by the other agents, a potential new neighborhood. So at each step, the agent has already some actual friends, so he has a group of actual friends, and he selects a new group of potential new friends. So you see, in the actual friends, you have the blue man, the yellow woman, and the violet man, and in the potential new friend, you still have the blue man, and you still have the yellow woman, but you don't have anymore the violet man, and you have instead the pink woman and the orange man. So what the red woman is doing is asking how much would it cost me connecting with a new friend, and how much benefit would I get from these new connections. And then the rule of the game is very simple. If the benefit is smaller than the cost, I remain with actual friends. If the benefit is larger than the cost, that is, it is convenient to me to move, I will move to the potential new friend, as it is schematically illustrated in the figure. So the decision is based uniquely on the balance between payoff in doing this move and the cost function. So what I have to define now is a cost and a payoff. Cost. The cost is very simple. One can imagine that a node V has to pay some unitary cost C larger than 0 to maintain a connection with another node. So the cost is simply the number of connections the node is doing. I repeat, I'm doing here a zero model. The model can be enriched in many, many ways. But this is really a very, very basic model. So I have a unitary cost in maintaining connection. So I have K connection, and the cost I have to pay is K time this unitary cost. As for the benefit function, instead, the idea is, once again, that we are dealing with social networks. So what is the aim of any rational agent in social network is to increase their importance, their visibility inside the network. Everybody wants to be an influencer, so to say. So how can we frame this goal? By means of the betweenness centrality. So the idea is that I am a node V. I want to be in between all possible shortest paths that are originating in node S and ending in node T. So the idea is I sum over all pairs S and T the number of shortest paths that are using me as intermediary divided by the number of shortest paths. So the idea is how much I am important in mediating the relationship between any possible pair of nodes. You see immediately that this betweenness centrality has a problem, and the problem is that the contribution of the betweenness centrality of node B does not depend on the length. So it is one, the same, regardless on whether the shortest path between S and T is very large or very small. Now you understand that if I am the only intermediary between S and T, I have a very important role in the network. But if I am one of the many other intermediaries that there are between S and T, the role has to be a little bit different. So we decided to adopt as a model 0 the weighted betweenness centrality, which is nothing than the betweenness centrality multiplied by a function of the length of the path between S and T. And this length has to, and this function has to be a strictly decreasing function for what I just said. That is, the shorter is the shortest path, the larger is the weight that I have to give to this expression. So the game is very simple. So I have now the cost function, I have now the benefit function. And with these two simple rules, what I can do is I can evolve the network. Now, the network, after a transient time, converge to the Nash equilibrium. What is the Nash equilibrium? The Nash equilibrium is a configuration where no agent has something to gain by changing its own neighborhood. That is, all agents of the game have, in a sense, obtained their optimal neighborhood, their optimal configuration, in the sense that any move they would do in this Nash equilibrium would imply more cost than benefit. When this happens, it is easy to demonstrate by a series of theorems, three things in particular. The first is that the network has to contain necessarily at least one node of very, very large degree, a hub. And this node must be at the center of the network. That is, it must be in the structure of the network in a position such that any other node has a distance no more than 3 from it. And so you may immediately understand why 6. Because if I take any node in the network, I will have maximum 3 steps from the origin node to get to this node V. And I have another maximum 3 steps from this node V to reach the destination node. So this implies immediately that the shortest path between any 2 pair of nodes must be bounded by the number 6. And so the diameter of the network, the maximal distance, is exactly 6. So I repeat, this is a series of very heavy theorems. In the following, what I want to do is concentrate and to describe to you the main ideas that are behind this game. And in order to speak of the mechanism, I need to introduce the concept of L-independent sets. What is a one-independent set in traditional graph theory? So if I have a graph, a network, I can call a one-independent set, which is sometimes called also internally stable set or anti-clique, the set of those nodes such that there are no connections between them. Okay, so it's the set of vertices such that any pair of them isn't connected by an edge. So if you look, for example, to the picture, you immediately see that the nodes A, B, C, D plus the blue nodes form the one independent set. Because if you take any pair of these nodes, you don't have a direct connection between them. But now let us generalize this definition and designate as L-independent sets, SL, the set of networks nodes such that the distance between any pair of its member is larger than L. So, for example, the two-independent set is the set of nodes such that there are no connection between them, and there are not a unique intermediary between them. I hope you can see the mouse. So this means that A, B, C, D are forming the two independent set, because A, B, you see, you have two intermediaries, the red nodes. A, D, again, two intermediaries. A, C, two intermediaries. C, D, you have many more intermediaries. But the problem is that the distance between any of them is larger than 2. So it's evident from the description I gave that if nodes belong to the L-independent set, they certainly belong to L-1 independent set, but not vice versa. So you can have nodes that belongs to SL, but they do not belong to SL+1. For example, again, if I consider the figure, I have node A, B, C, D, which were part of the one independent set, which are also part of the two independent set. But the blue node, you see, the blue node are not part of the two independent set. They were part of the one independent set, but not of the two independent set. Because, for example, between this blue node and D, you have a unique intermediary. So the distance between this blue node and D is 2, not larger than 2. Okay? So this figure illustrates the comparison between the two independent set and the classical, so to say, one independent set. Why this is important? This is important for the following way. Suppose that now we are in the Nash equilibrium. We run our game and we obtain, and we are in the Nash equilibrium. And suppose that we are considering two nodes, node 1 and 2, which are in the one independent set. This is illustrated in figure A here. What does it mean they are in the one independent set? It means that there is not a connection between them, but there may be several intermediaries, 3, 4, 5, 6, that are forming the shortest path between 1 and 2. And now let's suppose that an external node, 7, wants to form a connection between 1 and 2, bridge between 1 and 2. This is a legitimate move of the game. And this move should be prohibited in the Nash equilibrium, because otherwise we are not in the Nash equilibrium. The question is, which is the gain of node 7 in forming the yellow connections to 1 and 2? That's very simple. This gain is very little, because by forming this extra yellow connection, node 7 is not removing node 1 and 2 from the one independent set. So node 1 and 2 remain in the one independent set. The only effect of this connection, this yellow connection, is to increase the multiplicity of the shortest path between 1 and 2. So initially there were only 3, 4, 5, 7, 6, and now there is another 7. So the gain, which is due to the shortest path between 1 and 2, should be divided between all of them. So 7 is taking one part, one little part of what initially was instead given to node 3, 4, 5, 6. What does it mean? It means that in the Nash equilibrium, this node 7 has a very little gain, so consistent, large, one independent set are possible inside the Nash equilibrium. A completely different situation occurs when you consider the picture B. The picture B considers two nodes, 1 and 2, which are in the two independent set, not in the one independent set. Which means that they have not a direct connection, nor a unique intermediary. This means that you have node 3A, 4B, 5C, and 6D, which form the shortest path between 1 and 2. And now suppose the same, that an external node 7 decides to bridge node 1 and 2. And now you can ask yourself, which will be the gain of node 7? So in this case, the gain of node 7 will be very large. Why? Because by forming the yellow connection, what happens is that node 1 and 2 are removed from the two independent set and goes in the one independent set, because now 7 is the only intermediary between 1 and 2. The shortest path is done through 7. Which means that 7 acquires all the gain that initially was distributed in all the possible shortest path, 3A, 4B, 5C, 6D. And those other shortest paths are not anymore the shortest paths, so they lose completely their gain. This means that this move is extremely convenient, and this also means that by a theorem you can demonstrate that two independent sets are incompatible with the Nash equilibrium. So in the case of two independent states, the node 7, which eventually will be the famous external node, is reducing the distance of node 1 and 2 from 3 down to 5, and it's therefore obtaining a very large benefit. So this move is in principle possible, and therefore this move is incompatible with the Nash equilibrium, and sizable two independent sets cannot exist in the Nash equilibrium. So the fact that two independent sets cannot exist in the Nash equilibrium leads immediately to the fact that node 7 is a central node. Why? The question is, if I now consider node 7, which now forms the two connections between 1 and 2, can a node in the network exist in the Nash equilibrium at a distance to node 7 of 4, that is larger than 3? And the answer is no, because for this node to exist, it means that the shortest path from 7 to this node must involve one of these nodes, 2, and another 2 nodes here, because you need 4. So you need 1, the yellow, 1 to 3, for example, 3 to this intermediary node, and intermediary node to question mark node. But if this would be the case, this question mark node would be in the two independent set with 1 and 2, because again, and we just saw that there is a limit for the two independent set in the Nash equilibrium. So by means of I repeat, this is if you are interested in the mathematical details, you have to go in our paper, which was published in Physical Review X last year, and it contains a series of theorems that states fundamentally this. You can prove that just by balancing cost and benefits, the Nash equilibrium is incompatible with sizable two independent set. And the fact that it is incompatible with sizable two independent set implies immediately the existence of a node like node 7, such that it has a large degree because it bridges all possible two independent set in the network, and it is such that any node has a distance maximal 3 to it, and therefore you have 6. So the reason of 6 is because 6 is nothing but 3 times 2. So you have 3 steps to do to go to the gluing node, and then from the gluing node, 3 other maximum steps to do to go to any other node. And just to prove that this is indeed the case, I skip all details. What you do is the following. So let us, for example, take an initial ensemble of nodes. So here you see in this axis, I put the sides of the network. So I start from network of very little number of nodes, about 10 nodes, up to 10,000 nodes. And for each value of the size, one generates 10,000 different realizations of a scale-free network, a network where the scaling is a small word and so on. And so you have an initial ensemble, which is the blue ensemble, in which you have 10,000 different realizations for each size of network having a specific scaling, which is the one given by the Barabasi-Albert preferential attachment. Then in this ensemble, you can calculate the average D, that is the diameter, and you observe what you expected. That is that you have a very nice logarithmic scaling with the sides. So the sides the diameter solely increases logarithmically with the number of nodes, and this is reflected by a very nice straight line in the log linear scale. Then what you do for each one of these conditions, you take this as initial condition, you run the game, you wait for the game to have reached its equilibrium, its Nash equilibrium. That means you wait for the game to stop. I mean, for the nodes not to be able to do any new changes. And you obtain a second ensemble, which is the ensemble generated by the game once applied to the initial conditions of the blue line. This second ensemble is the green ensemble. And as you see, the diameter this time increases, then it goes to 6, and then remains 6 independently on the sides of the network, which means indeed that by means of this compensation rule, you are renormalizing all the distances in the network in a way that 6 appears as to be the sides independent maximum distance between nodes. Then one can argue that, of course, if you start from some initial condition and you change the connections, you are changing the density of the network. This you are maybe adding new connections or removing new connections. So you are, in a sense, changing the density of the network and therefore also the structure of the shortest path. So what we did is, okay, we go back to initial condition, we reinitialize the game, and we take note during the game of the number of links which were added or removed during the game, because during the game you can add, remove, add, remove, add, remove. So you have at the end, when you arrive at the final state, at the equilibrium state, you have a given number of added link, given number of removed link. And now we go back to the initial condition and we add and remove this exactly the same number of links, but now randomly, that is without checking cost and benefits, just randomly. And you obtain a third ensemble, which is the red ensemble, where you have randomly added link in the same proportion as those added and removed during the game. And of course, this second ensemble has a diameter which is smaller than the blue one, but still is scaling logarithmically with the sides. So the only way you can have a network which grows in size and nonetheless the distances are renormalized are at the equilibrium state, at the Nash equilibrium state of this very simple compensation rule. Oh, let me comment something, because we had, of course, contact from people that are strongly inside social network. You see, the rules that we are putting are really zero rules, very, very simple. So you have a cost and the benefit. And the benefit is, the idea is that if I am node V, I incur a cost to realize a connection with another node, and this other node cannot refuse the connection from V, which is completely different from what happens, for example, in social network. Normally, for example, in Facebook, what you have is to propose a friendship and the other has to accept. So it's evident that the cost and benefits are not cost and benefit related to one node, but it's a sort of mutual cost and mutual benefit that is the driving force. But we wanted to show really a sort of zero, very simple, very basic, very fundamental mechanism, which is still producing the 6 degrees of separation. Last comment, which I have many comments here, because we of course compared this mechanism with other growing mechanisms and we found fundamental differences. But the important point is another one, is this. Sorry, I'm trying to, no, The important point is contained, the important, I mean, discussion and conclusion is contained here. So basically what you have here is that 6 degrees of separation emerge as a natural consequence of a compensation mechanism between cost and benefits. And you can imagine that this indeed is a natural interaction strategy of rational agents. That's why you observe these 6 degrees of separation in social networks. Still, you can imagine if you don't have a social network, but you have, for example, man-made network, like technological network. Well, this compensation of cost and benefit can be also a driving mechanism in the design of such networks. Imagine, for example, transport network. So you have air or sea transportation networks. In these networks, the nodes are airports or ports, and they may increase indeed their volume of trades and or of tourism by being in between the main routes of interchanges of passengers and goods. So you can imagine that you can take the main mechanism, the same game theoretical approach, to optimize the design of technological network to make this transportation network to be such ultra small world, to have such ultra small world property. The third class of networks are biological networks. And here, you cannot claim that biological units are rational agents. Proteins in a protein-protein interaction networks of genes in genetic networks are evidently not rational. So you cannot argue that the between centrality has a role in the shaping of the structure of such network. However, you can imagine instead that you have other compensation mechanisms that could have played fundamental roles with different benefit function. For example, evolution, these biological networks are the fruits of millions of years of evolution. Evolution is based on random mutation and then on selection process. So the selection process normally selects the most resilient structure of the best efficiency that you have. So you can imagine that if you imagine to take as benefit function the resilience to random perturbations or failures or the local or global efficiency, you can, and still you have a cost involved in making, you can still create a game which shapes a network in the way, in the Nash equilibrium of this game, in the way you see today biological network. And this is exactly what we are now working, try to see if we can, in a sense, recoup for the cost of forming or maintaining a specific adjacency structure also in this case, and we can reproduce some aspects of biological networks by simple game theoretical rules. I finish here. I think, I don't know if I consumed all the time. I think I consumed. And so I'm very happy. I will be very happy to answer questions, if any, or any doubt and things. Thank you a lot.
Thank you. There are several questions posted to the chat throughout the talk. I would like to invite Yuri if you want to ask your question yourself, or would you like us to ask a question? So I will ask a question. So this is a question for after the talk. Since agents can perform actions, then this sounds like a potential source for non-conservative nature, i.e. driving the system out of equilibrium. My question is there always a Nash equilibrium state, or can we get some non-equilibrium state that are stationary in the sense of distribution, but with some sort of currents between subsets of nodes?
This is a very good question, and indeed, you are not guaranteed always to reach a Nash equilibrium. Normally, when you have compensation rules, this always happens because it means that you have some minus plus, so to say, compensation. But if you put together other driving mechanism in a game theoretical approach, you are not indeed guaranteed to fall into a Nash equilibrium. In our case, we numerically see all the times that we reach the equilibrium. We didn't prove in the paper that but we prove that whenever you reach the equilibrium has 6 degrees of separation. I see here there are many other messages.
Yes. So, Matteo, would you like to ask your own question or?
I see what is the number of hubs of central nodes? Are they stable, or during the evolution can one node become of course it can become a new hub at the expenses of an old hub. Yes. So you have from the initial condition you have a final state where nodes are different because you have a redistribution of the structure, and yes, and you can have more than one. Actually, what you can prove in the theorem is that in the Nash equilibrium you have at least one hub. But of course, you can have many hubs, not only one.
Okay, thank you.
I'm going to ask Matteo's question. Does this mechanism change the way the total number of edges scale with the size of the network? Does this mechanism change
Yes.
the way the total number of edges scale with the size of the network?
The total number of agents?
Edges. Edge.
Edge. Yes, of course. And that's the reason why I took note exactly of the number of edge which were deleted and which were added, and I compared with the corresponding, if you, maybe I can, because, sorry, I share again. So in this figure, what we do, you see this figure?
No, we cannot see your screen.
Let me see if you now, is now possible to see the screen?
It says double click. No, not yet.
Not yet. So let me see what is happening. Stop sharing. Let's reshare again. I have to share the entire screen. Okay. Now it seems I'm sharing. And now I have to go back to the presentation. See the presentation now?
No, we cannot.
Well, if you remember, there was a curve in which I defined 3 ensembles. One were the initial condition, the small world. The other one was the equilibrium state that was reached. And the third one was the one that you reach from the same initial condition by adding and removing randomly the same number of links that you add and or remove during the game. So that is without compensation. And of course, during the game, you are changing the density of the network. You are changing the number of edges of the network. But in both cases, I've shown that the scaling continue being logarithmically with the size. Therefore, the more you increase the size, the more you deviate from 6.
Thank you. By the way, your screen showed up. There's just a delay. Doug, would you like to ask your own question, please?
Sure. Thank you. So, Stefano, thank you for this
Yes.
great talk. That was really nice. And congratulations on your fellowship. So I had a couple questions. The first one, I'm an experimentalist, so I'm interested in data. What's in all these great experiments, what's the distribution of distances? You said the mean is 6. What's the distribution? And as a
Not the mean, the maximal.
I understood it to be the mean.
No, the maximal. The diameter is the maximal. Is the
That's in your
maximal.
argument.
Yes.
But from the experiments, I understood that to be the mean.
From the experiment, you have the mean, which is smaller than 6, and you have deviations. I have to tell you that in the experimental data, the deviations are not so big. They're not so big. They are sort of Gaussian distribution. So when they have the mean, they are very... So there are not large tails, so to say, in the experiments I've shown at the beginning of the talk.
Okay.
So it seems really that you're right. I mean, one thing is speaking of the mean, one thing is speaking of the maximal, but in the experiment, I mean, the deviations are not so huge.
Good.
There are many other social experiments in which they try to understand if these distances varies with the status of the person. You know, if you want to reach the Pope, or you want to reach, in some social network, you are professor, you want to have another professor, same status, different status, but it seems to be rather homogeneous, the distribution.
Okay.
I saw another. Sorry, the second one.
Yeah, no, I was going to say I have another one, but I should let other people ask first.
I saw another question here, which is very interesting. It's in your talk, you have basically individuated, again, theoretical approach means that they are completely rational. But in fact, humans are not rational, so they sometimes take decision based not on rationality, but on, I don't know, many questions. That's a very, very good question. And the truth is that I have not yet thought how to incorporate irrationality or variability of such rationality into the game. But this is very, very nice if you really want to understand, I don't know, political elections, for instance, the outcome of political elections, so something like this. So some other questions?
So Menon has a question, and then John has
I just had a question about how much information was left when you found this very, very strong equilibrium. You've told us that one number is extremely stable, but you erase all information about what cost benefit was assigned by actors in this, or do you still have some non-universal features that can help you pull out that information?
I repeat, we try to really, there was no models up to us where the diameter of a growing network was independent on the sides. And this was our motivation. So as a physicist, we want to have really a basic model. You are right. We took one cost function, one benefit function. So in a sense, we didn't demonstrate that how universal it is. I mean, you can take different cost function, benefit function, and so on. I think that for the theorems that are inside, whatever cost function, well, cost function is reasonable to imagine that you really need to have a unitary cost in forming connection. This is true for biological system because you have a price to pay to create a connection. It's also valid for technological imaging, I don't know, power grids. You have to really put a cable from one to another one, so it has a cost. And also for social, because you have a limited time. So if you have 100 friends in Facebook, you have to chat all the day, or, these things. For the benefit function, whatever function is based on distances, on shortest path structure, is important. Because the main idea, I repeat, is that you impede, you impede to the two independent set to form in the Nash equilibrium. So if you have similar, not between the centrality, but you can have other benefit function which involve the structure of shortest path, and involve the fact that you want this shortest path to pass through you. So you want the shortest path to involve you. You want to be central in the information flow that you have in the network, so to say. Because the shortest path, you can imagine for example, any diffusion process like a random walker is diffusing along the shortest path. So you want to be at the center of the network. Then it will work. It will work because at the very end, it will impede the formation of two independent sets in the Nash equilibrium. And this is the key of the key idea, that you have to recompact and to have this normalization of distances, which produce eventually a diameter, a maximal distance, which is independent on the sides.
Thanks, it's very helpful.
I have a question. So this is done in the topological framework where you don't have preference over the distances. So if we try to do this in an Euclidean framework where you have geometrical distances coming in, how do you see this diameter growing? Is it a reasonable question?
No, it's a very important question. I repeat, normally in social network, you don't have a distance, because you have a friendship, for example, with a person in India, or a friendship with a person in Italy, or a friendship with a person. So it's independent on the geographical location. When if you consider technological network instead, then you have a physical distance between, or also biological things about the brain. You have and the cost that a neuron has to pay to connect with a close-by neuron is less than the cost that the neuron has to pay to connect with a far-away other neuron. So all these things are, of course, to be taken into account in a much more refined approach. And it's very interesting, for example, also because the concept of the shortest path changes if you are, in this case, you have a weighted network, because each link is based on a physical distance. So the shortest path is not generally the number of steps you have to do, but the real distance that you have to make, no? Which may be different in some cases.
Yes. So yeah, it's very interesting. Yeah.
But I repeat that this is something that indeed is going to enrich very much the model, and also difficult a little bit the demonstration of the theorems, but it's something that it has to be done. Yes.
Another small addendum to this. These results, are they available in archives, or is it going to be published soon? I might have missed
The paper is already published 2024 in Physical Review X.
Okay, thank you. I'll look it up.
It's an open access, so you can get it.
Oh, thank you, Professor Boccaletti. Thank you.
Thank you a lot. There was another question by Professor Durian.
Oh.
He said, I wanted to have the others, but now the others already asked it.
Well, you actually answered it. You read it and answered it. So
Actually,
thank you.
I had one more question, though, if I could. I guess the distribution of benefits would be uneven. The hub would have end up with more benefits if you look at it, each node and what benefits do they have in terms of centrality or betweenness and so forth. Would that be a potential mechanism of instability? If everybody wants to be the hub,
That's not necessarily true.
Okay.
There is a fundamental difference between in networks theory. There is fundamental difference between degree centrality. The hub, of course, has much more connections, and betweenness centrality, which is to be in between. For example, I make you the very simple example. Imagine that you have 3 nodes, 2 external nodes, like here, 2 nodes here, and they are both hubs. So this node here has 1 million connection, and this other node has another million connection. But they don't have a connection between them. There is no connection in between. And now there is a middle node here, which has only 2 connections, one to the right, one to the left. Okay? So this node has only degree 2, only 2 connections, and these other nodes are only 1 million connections. From the point of view of degree, of course, the 2 hubs are much higher ranking than the node in the middle. But from the point of betweenness, they're exactly the same, because if you take any pair of nodes, one being connected with this hub and the other being connected with the other hub, the only way to form a path between them is passing through the middle node. So the middle node has an extremely high number of shortest paths that pass through it.
Mm-hmm.
So not necessarily the hub has the best benefit in terms of betweenness.
But why doesn't that lead to kind of an instability mechanism where, another one wants to be in that sort of, connect the hubs, and more nodes try to insert themselves there as they get the largest benefit?
Yes, in principle, you're right. I mean, as I told you, there is no guarantee. We didn't prove in the paper, we could not prove in the paper, that with these rules, you always get to an equilibrium. So probably there is this instability but what we observe numerically that we always go to an equilibrium. And what we proved in the theorem is that once you get to the equilibrium, then the equilibrium has to have 6 degrees. When you are in the equilibrium, you cannot do any move. It means that any node in this configuration, if they change, if they do any extra connection, they would pay more with respect to the extra benefit that they would gain.
But that means you couldn't have the situation you were describing with the sort of 2 equal hubs.
Yeah, you can have this distribution, which is very pathological if you want. Yes, you can may have frustration. For example, if you have 2 big influencers, this is the case of 2 big influencers. Imagine 2 big football players, Ronaldo and another one. So Ronaldo launch in his own social network tomorrow. All my followers, they should buy blue shoes. And the other says, all my followers should buy red shoes. And the one in between receives these 2 contradicting inputs. So which shoes is buying, or maybe he's not buying any shoes. I don't know. So it's true. I mean, there are cases like this. You may have cases like this.
Maybe this is a good time to bring sort of the formal question period to an end and thank Professor Boccaletti again for a very nice talk, and one which addressed a brand new result, and like all great brand new results, open many new questions also.
Thank you a lot to you, all of you, for the patience and the time you dedicated. And as I said at the beginning, I will be in the APS March meeting. So if any of you will be there and in our business meeting, it will be a pleasure to meet you personally.
Thank you.